Good afternoon. My name is Anthony Zamaro. I am with DuPont Water Solutions. Um, I am a MBR product lead for DuPont. That means that I get involved in business development, new product launches, um, and also I do a lot of work with existing customers, just making sure that everything's working great and that folks have a good experience with the product. I also do a lot of this. I do a lot of presenting. Um, Today I'm going to be presenting Ready for Implementation, the evolution of membrane bioreactor systems. Um, the genesis of this presentation was a set of slides that I've presented a few times that talked about something called the Gartner hype cycle, and it's a model that's used in software engineering to describe new technologies and how they're adopted and roadblocks that come in along the way. And using that model, I've developed this presentation where I talk about the three generations of MBR technologies. But I'm going to start out with just what is a membrane bioreactor, just to set the stage, so to speak, give a very brief history. Then I'm going to talk about the Gartner hype cycle and the three generations. I'm going to give you a few case studies, one from each generation, and then talk about what's next in MBR technologies. What is a membrane bioreactor? So a membrane bioreactor, very simply, is a bioreactor with a membrane at the end of it. So it's not one or the other. It's not a bioreactor or a membrane. The membranes aren't separate. They're kind of a symbiotic process where you need both. And what's really going on, I really like this slide because it demonstrates you have a biological system in a traditional MLE process where you're doing your biological treatment with microorganisms, and then you're settling. And really, in that settling step, you're sending solids back to the biology because you don't want to lose your bugs. And then, in some cases, you'd have a filtration step afterwards. The traditional MLE process is a hydraulic process because what you're trying to do is you're operating for settleability. In an MBR process, it's the same general principle of operation. It's microorganisms in a tank getting oxygen and eating waste. The difference is that instead of a clarifier retaining your biomass, it is a membrane. And what that allows you to do is you don't any longer have to worry about settleability. That's one advantage. The other advantage is you get that filtration step in the same unit operation. It's not two unit operations, it's one, and you're getting a much higher quality and much more consistent product. But the important thing to remember is that it's still the same process. It's still MLE or Cape Town process or simply a bioreactor, whatever it is, but you're retaining the biomass in these membranes. So you're decoupling SRT and HRT, solids retention time and hydraulic retention time, and it allows you to increase your hydraulic retention time and your solids retention time in this process. And then the part of it I mentioned, the membranes of the bioreactor are one single piece, but when we talk about just the membranes, we call them a membrane operating system. You may hear me use that phrase in this presentation. I call this slide the Acme membrane bioreactor just because 80% of what we build is this. It's an anoxic zone. It's an MLE process with membranes at the end. So a couple of things to note here, just like in a clarifier, you're sending liquid forward, you're sending mixed liquid forward, and you're returning. So there's a loop here. It's a little less than a clarifier, like 1.5 to 3Q, but this is a 4Q return, or 4Q forward, 3Q back, and 1Q of filtrate. Q, in this case, is the flow coming into the plant. We want to match that in the effluent, but we're continuously recycling. And the reason for that is membranes would act as a dewatering system. If we just left liquid in here, kept feeding liquid to this tank, eventually the water being removed through the membranes would cause solids to accumulate here. So we need kind of a refresh stream to keep things moving. The concentration in your membrane tanks, just because of a mass balance, will be higher depending on the Qs, the Q ratio here. But it'll stay at a manageable level. Sometimes, again, I call this Acme because it's the most common, but you can have 5-stage Barton-Faux. You can have MLEs. You can have anything you want in the bioreactor. Sometimes there's internal recycles, et cetera, et cetera. Sometimes there's deox zones after the membranes because you don't want to poison, say your return is going to an anoxic or an anaerobic zone. But this is generally what we do. It's a pretty simple and straightforward process. This is a membrane pore size reference chart. We have the membranes my company makes are ultrafiltration membranes, so they're 0.04 micron. That's what this red line is. Some membranes in MBR, which are fine, are microfiltration. They're different, and you might get different results, but there's nothing wrong with those membranes. But what we're trying to show here is the type of particles that would be excluded by these membranes, which is basically anything to the right is what's excluded by these membranes. So there's a lot in there, and there's some things that aren't, notably salts, metal ions, atomic particles, obviously. But membranes, ultrafiltration membranes are designed to remove solids. These are all particulates, these particles. So particulates are suspended in solution, they're not dissolved. So things like nitrate, dissolved TOC, those are on this side of the chart in that they're dissolved or molecular, and they're not going to be retained on the membrane. So the membranes are purely to retain solids, which is a lot of stuff in a mixed liquor stream, but not everything. So this slide is intended to just demonstrate kind of the principle of operation of MBRs. When MBRs were first introduced, people didn't think they would work because in most conventional membrane filtration processes, you're limited to about 200 ppm of solids. And in a mixed liquor environment, at the time when they were thinking about MBR, it was 2,000 to 3,000, as we talked about with conventional mixed liquor treatment. The way these membranes are made to work is through the principle of solids back transport. So what that means, filtration is occurring by creating a suction pressure. This is a hollow fiber membrane. It would be analogous in a flat sheet membrane. I just use this because it's the type of membranes my company manufactures. But these are membrane tubes where this blue here represents water. This is a membrane. So what we're doing is we're pulling a suction on the tube part of the membrane that draws mixed liquor to the membrane surface and allows filtered water to pass through. So we're transporting via that suction pressure mixed liquor to the membrane surface. That mixed liquor consists of solids and liquid. As you pull mixed liquor through the membrane and clean water leaves, what you get is what's called a concentration gradient. That means that solids start to accumulate at the membrane surface, and it creates something called a cake layer. The cake layer is actually a pretty cool thing, a pretty cool dynamic, because it actually provides some protection to the membrane, both on a chemical basis and from damage to the membrane. But if there's too much caking, the membrane will be choked off and it will become impermeable. Permeability is a measure of how easy it is to pull water through the membrane. Impermeable means you can't pull water through the membranes. So the solution is create a back transport of solids away from the membrane surface. It looks like my little video is blocking some of this. But the air and mixed liquor, so this is the air scour that happens in MBR, and this is what made this technology really possible, is the idea that we could use air and mixed liquor in a cross flow to the membrane. It means perpendicular to the membrane surface or orthogonal to the membrane surface. We're pushing air and mixed liquor that pushes the solids away from the membrane. So you're just mixing. It's just mixing energy. And it takes some of the solids and it provides a back transport away from the membrane. And that's what makes membrane bioreactors possible. But it also creates the biggest issue in MBRs, which is solids accumulating inside the matrix of the membranes. If your air scour is inefficient, you will have to do manual cleaning of the membranes. Okay, so a short history of MBR technology. Again, this is very short. A company called Dorr Oliver did some testing with side stream MBRs in the 60s. Side stream is literally, you would take a bioreactor and you would have a stream of water coming out of the bioreactor, going to a membrane and coming back in. So it created a little circuit, and the membrane would draw a little bit of clean water all the time through that little circle. So what the advantage of that is you get great mass transport through that little circuit, but they weren't very space efficient. They weren't immersed in the mixed liquor, so they didn't. You had to like pump it through these little tubes. So you had to have multiple little tubes to make it work. So it didn't really go anywhere. People knew it worked in principle, but it didn't go anywhere. It wasn't commercially viable. So the Japanese government in the 90s launched a program in Japan. There's a high population density, a lot of small sources of wastewater, malls, and urban centers. So they wanted some technology that would have a small footprint. So they funded a project which turned into the Kubota membrane. They licensed the technology to Kubota, and Kubota started making plants in the late 90s, early 2000s. A company called Xenon developed a product. They actually bought this, I believe, but they developed it for the technology. It was called Moustic. It was an unusual fiber. This is a diagram of it here, the Moustic module or Moustic fiber. And they were treating oily wastewater initially, but then saw the potential to move into municipal wastewater. And then we all started kind of getting into actual applications. Cred to Kubota and Suez. They're called Suez now, for being kind of first to market. We were soon after them in 2002 with our technology. And this is what I call the first generation. We'll get into that, but these were very early, and in a lot of ways the technology was still in development. So this is where we get into the product adoption curve. So this one is kind of it's like a generic product adoption curve where you have innovators, adopting the technology first, and you have some early adopters, and the development goes like this. It's a nice curve. It peaks and then starts to fall off as new things are developed or whatever, right? Or new technologies, and it becomes an old technology by the time you're here. This is kind of what most products, or maybe it's just simplified, but Mbr definitely did not follow this curve. This is the Gartner hype cycle, which I referred to, and this much more resembles what happened with Mbr. So the principle here is that somebody comes up with a cool new technology. Again, this was intended for software, but it applies here. They develop a cool new technology and they start developing offerings to the market. And there's an adoption curve. And this isn't volume of sales, it's expectations is the y-axis here. So people were really excited. We'll just hop into the Mbr analogy. People were really excited about Mbr. We got first generation products. People start, early adopters investigate. You got people starting to build plants. Just some media hype. There was media hype, believe it or not, in the early 2000s. Supplier proliferation. You got people adopting, and then negative press begins, right? And then failures. And that definitely happened in Mbr. So I identify 3 generations here in this curve. The good news is, right, before we get into what went wrong, is that we're in the 3rd generation. That's the upshot here, and that's why this presentation is called Ready for Implementation, because a lot of the issues have been worked out, and we have great products, but we're going to go through kind of the history of how we got to where we are. So first generation Mbrs, the very early designs, both Kubota and Xenon, were immersed in the biology, meaning there was not a separate membrane tank. The membrane sat in the mixed liquor. There were some advantages to that. You could just pop them right into an existing bioreactor and get that capacity. A lot of early plants did that. We were the first to, my company kind of grew out of drinking water membranes, so we just had a different philosophy of operation and cleaning. So we wanted to have a separate membrane operating system. Remember, I used that phrase earlier, so that we could do chemical cleans. Design criteria varied widely. We had SRTs all over the map, and the big thing was MLSS. Right now, to kind of give you a preview, we run about 10,000 ppm. People were going up to 25,000 in the early installations, and flux rates were all over the place. There were a lot of people that thought, it was early enthusiasm, it was before my time, honestly, but people thought these things could do a lot more production than they were actually capable of. Mostly small systems, early adopters. This is a picture of we call this an express plant. It's an early express. It was a product my company made. But this was common. Package MBRs were common, and issues. So fouling was a big issue. Process control was a big issue. So things happen at a microscopic level in membranes that are hard to predict, and they happen over long periods of time. So these early adopters, we developed applications and processes that would work well for 6 months and then run into roadblocks, and we weren't sure why. And then support services, this is kind of a preview. This became much more of an issue later, but screening and cleaning equipment became an issue in these first generation MBRs. So second gen MBRs, the technology started to be adopted more widely. And what I really feel like is the defining criteria of these second generation MBRs is that we settled on process set points. So I say they converge here. This mixed liquor concentration, the flat sheet guys run a little bit higher, sometimes they don't, but really we're around 10,000 as an industry in the membrane tank. Flux 10 to 30 GFD. This is realistic and it's consistent across different membrane technologies. There are advantages within different membrane technologies for various reasons, mostly hydraulic, but within this range, we all operate pretty closely. I'd say within 10% of each other from a flux perspective. Larger systems started to be built, and as we started building larger systems, there were issues. So the big issue was power, efficiency here, I call it. But the second gen plants used a lot of energy. They used about 6 times what we use today for air scour, for that solids back transport that I talked about. Process control and cleaning, also issues. They've always been issues, but really the biggest thing here was screening. Screening was a huge issue. Most wastewater operators, when you start talking about membrane bioreactors, their first kind of focus is on how fine are the fine screens going to have to be. And I think in this second generation, again, this is a little bit before my time, I started coming in right at the tail end of this. I think there were compromises that manufacturers and operators and engineers made to try to make that fine screening question as manageable as possible. And the biggest thing was the type of screens that were approved and the redundancy requirements on those screens. So, for example, this plant is in Hillsborough, California. I'll talk about it a little later. They had issues with their core screen. Their fine screen was too fine, so the fine screen blinded off, and they had to bypass it to get capacity. So all the trash from the fine screen just went to these membrane tanks. Other plants in this generation used a band screen, and the band screen, kind of an in-channel or out-of-channel drum. In-channel or out-of-channel band screen. And the issue with those screens is they would put 1 or 2 millimeter perforations on the screen itself, but the seals between each panel would be 5 millimeter, or they would stretch to 5 millimeter if they weren't already. So very quickly you had that hydraulic bypass where the mixer wasn't going through the perforations, it was going through the seals. That was very common in these second generation plants. So this is kind of the result, and I mentioned back transport being kind of the key in MBR operation. I'm not showing these. I think one of these is my membrane, so I'm not trying to pick on any suppliers here. This one is a flat sheet system, I think. But I'm just showing here what happens when screening breaks down, right? Or when air scour breaks down. This solids packing, you don't need a PhD in membrane science to see that mixer is going to have a hard time moving through this matrix of membranes. And what happens, you see the fellow here with the blue gloves, he's going to be doing some cleaning, some manual cleaning, because this has gotten so bad that the aeration can't keep up with it. here we talk about the primary methods of limiting solids fouling. MLS concentration, that's one. Really screening is the big one. Membrane flux, how we operate the plant, is a big one. But really screening and air scour are going to be your main tools to prevent this kind of thing from happening. So third generation systems, this is where we are now. The plant here in the picture, this is Modesto, California. This was started up in 2015. So this is firmly in kind of the third generation. So here we talked about how we got to third. What is a third generation MBR system? Screening is largely figured out. Most MBR suppliers, I would say all of the major MBR suppliers, have converged on 1 to 2 millimeter for most applications. I often send around a presentation done by a PhD named Dr. James Mbr from Avivo. At the time, Avivo was using Kubota, and Dr. Mbr recommends 1 millimeter. And I'm not trying to call it Kubota. I don't know what they're doing today. But the point being that, like, everybody kind of understands that the tighter screens are better because they prevent a lot of the fibrous material from getting through. They prevent a lot of hairs from getting through. We don't have any bypass on the screens anymore. We have 100% redundancy size for peak hydraulic flow, meaning I got a screen out of commission and it's going to be a rain event tomorrow. I'm okay. Everything's going through the screen. Nothing's going to bypass the screens. And we've also kind of settled on technology and configurations that work well with MBR. The workhorse of the industry is an internally fed rotary drum screen, not an in-channel. In-channels are okay. We do them once in a while. But really, the out-of-channel drums are the best because they just have those two big seals on either side. There's very little to fail. There's plenty of hydraulic space in there. There are some really interesting band screens coming out now that have been designed for MBR, and we like those. But really, still, those internally fed drums are the workhorse. After 07, the focus shifts to lower energy. I mentioned those second-gen plants were using 6 times the air we use right now. Suez Xenon developed cyclic aeration. I believe that was a little earlier than 07, maybe like 06 or 05. They developed that. What that did is it turned the air on and off. It was patented. So what they did 20 seconds on, 40 seconds off, or vice versa. But they had valves at the end of the headers. These are air headers at the end here. They had valves that would actuate every minute, basically, or twice a minute. And those would wear out. So it was a revolutionary technology in the sense that it cut air by about half from when compared to second generation MBRs, but operators weren't big fans because it burned valves out pretty frequently. We developed Mempulse in 07. That was, I have a slide in here kind of explaining what it is, but it was a intermittent aeration system, but it didn't use moving parts. And since then, all of the major MBR manufacturers now use some kind of pulsed aeration. We all argue about who was first. I think I was first, but I'm not going to make a big deal out of it. Mempulse reduced air consumption by about 50%, and it's improved since then. But interestingly enough, around the same time, the market slowed down. So there was some, I think the second bullet point is actually the more important one. There was a general slowdown, but there was a bit of reticence about the technology. If you think back to that Gartner hype cycle, we had reached the peak and had some issues in those second-gen plants, a lot of screening issues, a lot of operation issues. So people had soured on the technology a little bit around that time. But fortunately, there was still interest. There were still really kind of non-negotiable drivers, let's say, for people still needing to use a membrane for treatment, fortunately, and that allowed us to kind of prove out these third-generation systems. So this slide is just showing that pulsed aeration. These are the 3 major hollow fiber brands. The hollow fiber guys all use this kind of pulsed aeration. Flat sheet guys, I think, still use, I'm not an expert, but I think they use a more continuous aeration. But all 3 of the hollow fiber suppliers, this is us, DuPont, Suez Xenon, and Koch, we all use some, they call theirs Pulsion, Koch calls theirs Pulsion, Suez calls theirs Leap, and we call ours Mempulse. But it's all in this drawing. If you look at this box at the bottom of the membrane, it fills with air. So there's a constant feed of air coming from the top of the module, fills this box, and once it's full, there's baffling down there to provide back pressure till it gets full, and then the whole bubble pops all at once. So it's kind of like that large bubble aeration. You get the best mixing energy at the lowest cost with a large bubble of air. All right, so some case studies here. Stevens Pass, this plant went in 04, is at a ski resort. It was a retrofit of an existing mixer treatment plant. So they had some reuse drivers. They wanted to do some stuff with the water, so they wanted to take their existing mixed sugar plant and do membrane treatment with it. So they used 500 micron wedge wire strainers. I say wow here because that was really unusual at the time. And some of it, I mentioned that DuPont came from drinking water membranes. So in drinking water, 500 micron is kind of normal, like that's the standard. So I think this 04 was before my time a bit, but I think that MEMCOR at the time was looking at this and saying, well, if we had that, that would provide a lot of benefit. So, but it does demonstrate in this first generation system, parameters were all over the place. Some people were using no strainers at all. But we had these 500 micron strainers. I think it has something to do with the longevity of this particular plant. It's done really well. There is a giant priming tank here, which was kind of a feature of first generation systems. We all had them. What it was a vacuum pump hooked up to this. There's a brown fiberglass tank, and it was attached to the filtrate header here. So when you stop filtration for a clean or something, the mixed sugar would fall out of this because it'd fall back to the tank level. This would be used to prime the header. So they'd pull a vacuum in here that would pull mixed sugar up back through this header so the pump could grab the liquid and start pumping. We've since eliminated those in second and third generation systems. So lessons from first generation systems. This is the Stevens Pass. We retrofitted these. This is our newest module. So we had a retrofit kit. That's important. When you have these older plants, I think, I'm pretty sure actually, I've heard of some of my competitors doing the same thing where they take older plants and they make a membrane available. I do a little bit of a commercial for what I call vertically integrated membrane companies where we build systems and make membranes. There's a few of us. We're going to develop packages for our older customers to make sure they can keep operating. This plant is 18 years old now, and we just put new membranes in. It'll be operating for a while. I think that a lot of plants, because of the gaming that went on with process parameters, had to be retrofitted or redesigned. And I say this process separated the wheat from the chaff. That's in terms of manufacturers. There are a lot of people that did MBRs in that era that aren't anymore because they couldn't kind of make that commitment to the market to make plants work. There are many plants from this generation still operating, I say, but not many. There are a few, but not as many as there were, let's say. Healdsburg, California, I mentioned this plant before. This was started up in 2008. So in kind of a cusp of that third generation, but it used MEMJet, which was my second generation technology, except in one cell. They were the beta site for MEMPulse in 2008. They had screening issues. I think I mentioned that their core screen was too open. So they had bypass go through and it blinded off the fine screens. Damaged membranes were replaced after that bypass occurred. And as part of that upgrade, they upgraded the other tanks to MEMPulse. They still have occasional issues with screens. They use in-channel drums. They had a bypass 6 months ago. So I talked about band screens already. I won't re-mention that. But that ability to upgrade to a new aeration system, which again, some of my competitors offer, some don't. I think many do. But an interesting thing about these second-gen plants is that they're reaching 10 plus years old, which is kind of the standard duration of a membrane warranty now. So what we have demonstrated, you talk about ready for implementation, is that we are able, this particular plant, this is Healdsburg here, runs the same aeration process and membrane that we've used since 2008. We've made incremental improvements to the process, some of the mechanical features, but if you bought a plant today, this is what you would get. and we're demonstrating 10 plus years of membrane life. They actually have 2 tanks at Healdsburg that are on 12 years right now. At Estill, California, this is my example of a 3rd gen system. This site is 12.6 MGD. They operate at 24/7. So a couple of things that are great about this plant. It uses turbo blowers for air scour. That's a great benefit. But really, what it is this Jennings Road plant is kind of a case study of ready for implementation, right? They have the right operators, they have the right equipment, they have the right screening, and a relationship with their supplier ongoing. So this plant's been running since 15. We started design in 13. So we've had a relationship with them for 9 years. They still call my techs all the time to talk about different things, modifying processes. If they run into minor issues, it's a phone call, changes to the HMI or something like that. So this plan is a success story. It's been running great. They have another system here that's been running 8 years, I want to say, from another manufacturer. So these guys are an example of how this technology works the right way. All right, what's next for MBR? I'm just going to run through this quick. My time is running out. Forward look at the market. Growth is huge. This is just me in the last 5 years, and these are just the big plants, right? For the most part. To us, 129 MGD, Changi 40 MGD, Rimini 40. We're going to be building a plant. Actually, it's Sarasota Bee Ridge 28 MGD max month flow. So 78% growth annually is what we're estimating, as a company. But more plants looking at IPR, DPR, it's driving investment, especially in bigger plants. Manufacturers continue to innovate. It seems mostly incremental, but we'll see. We'll see what people have up their sleeves. Ceramics are talked about a lot. They're real. I mean, there's ceramic installations, but they're still kind of working out the kinks, in my opinion. I think they're still on that first generation of development. Potable reuse trends, we're seeing this. You got Title 22, which has been around for 20 plus years. Tertiary UF, people are looking at doing something akin to these with MBR, and there's some big projects coming in. Singapore is doing 2 big plants. I talked about they're using our membranes in those plants. State of California has multiple demonstration plants going online. And when you talk about reuse, there are folks that talk about turbidity. Most regulators are attracted to some form of pressure decay test, which is a process where you pressurize the inside of the membranes to determine the integrity of them. So if there were defects in the membrane, if you pressurize them, the air would just leak out. But if membranes are integral, they should hold pressure for some period of time. We think turbidity and pressure decay are going to be the best approach to reuse and a potable reuse with MBR. Energy neutral MBR, this is a concept that's pretty interesting. But basically, using some type of solids capture, whether it be a high efficiency screen, these filters go down to like 20 micron, to remove solids and then send those solids to an anaerobic reactor to produce energy. That would be the concept, but there are advantages where if you're removing a lot of these solids, the membranes can run at higher flux because the screening is so good. So there's a lot of potential with this energy neutral MBR. It's still in development for the most part. And then anaerobic MBR, this is a big one where it's basically taking the same thing we talked about of taking a mixed liquor treatment system and putting membranes on it. You're doing that with an anaerobic reactor. So you have an anaerobic reactor where you're using membranes to retain biomass or to do kind of the decant function of an anaerobic reactor. And because you need to remain anaerobic or zero oxygen, you're using the biogas as scour air for the membranes. This is pretty interesting. It's mostly on food and bev technologies. There's a few people doing it. These ADI guys, they use our membranes. Suez is doing it. I think they just have their first installation in New Jersey or Delaware. And then Veolia, I'm not sure how much they're doing, but they advertise it. So that's it. Coming in just under 35 minutes. I want to thank you for listening, and thank you to the organizers for inviting me. And I'm available for questions in the Q&A. Thank you.